Hi, I'm Quinn, this is Declan and Connor, and this is our video for our final project in 359 Microcomputer Engineering. The project was given to us by Dr. Richard Klukas and Dr. Eman Nagar, and Declan's going to talk a little bit about it.
Alright, so the project requires to implement a real-world application with the TIVA C-Series development board using the skills and knowledge we've developed throughout the term. We chose to build a station which would track the angle of the sun throughout the day. Now Connor's going to talk a little bit more about our specific implementation.
So the station is made up with the board at its center, which is connected to a photoresistor to measure the light, and is connected on the side here with the stepper motor to adjust the angle at which the photoresistor is at. So as the light changes on the photoresistor, it gets processed by the sun tracking algorithm that we've placed on our board, and that outputs to the stepper motor and adjusts the angle so that it follows the brightest light. Quinn will now talk a little bit more about how the algorithm works.
Okay, so here we have the main loop of our sun tracking algorithm. We enter here, and then this upper bit updates our maximum value measured by the sensor. If it remains above 95%, we stay up here. If it goes below 95%, we move on to our scanning function. We determine 95% is when the sun is about 10 degrees off of our current position. So we need to locate the new position using our scan light function. So here's our scan light function, as mentioned in the previous flow diagram. We're going to have a measurement for the original position, then we're going to rotate clockwise, take another measurement, rotate back counterclockwise, and measure again. Once we have the three values for the counterclockwise, the center, and the clockwise, we're going to compare them and determine which one's the maximum. Knowing which one's the maximum, we're going to rotate to match its position, and then loop back and repeat the process.
Okay, so this is the photoresistor circuit that we use to measure the brightness of the sun shining on our project. It's composed of a photoresistor whose resistance varies from 150 kiloohms at the darkest to 150 ohms at the brightest. This component was put in series with a plain resistor of 10,000 ohms. As the resistance of the photoresistor changed with the brightness, the voltage across the 10,000 ohm resistor would change. We measured this by connecting node B up to pin PE2 on our TIVA board, which we had configured as an analog to digital converter. We attached the 3.3 volt pin on the TIVA board up to node A and grounded node C. This is the stepper motor drive circuit we used to control the stepper motor, which was rotating the light sensor I mentioned earlier. It's composed of 4 NPN transistors, the collector pin of each of which was connected to a supply voltage. We use voltages between 3.3 volts from the TIVA board all the way up to 10 to 15 volts from a benchtop power supply. The base of each transistor was connected up to control pins leading to the TIVA C board. The emitter of each transistor was connected to the wires that come off of the uniphase stepper motor. If you're not familiar with the operation of a uniphase stepper motor, what you do is you pulse or hold a voltage across each of the wires in a specific sequence. So if you want to rotate the motor in one direction, you would pulse at A, B, C, D, A, B, C, and then if I wanted to hold it at this position, I would just maintain a voltage at C, and it will try to keep itself there with a limited torque. To rotate it backward again, I would pulse B, A, D, C, B, A, and then hold my voltage there. We decided to use a stepper motor because I found it very easy to write a driver for in software, and its ability to rotate a specific amount and then maintain a torque at that location was very appropriate for our application. Okay, now we're going to demo the project. You can see as I move the light across the sky, the light sensor right here is going to try to stay at a right angle with the light. And as we move across, you'll be able to see that it has a full 180-degree tracking capabilities. All right. Thanks for watching, guys, and good luck on your projects.